अच्छी तरह भी आप चेक कर लीजिएगा. Okay, so I guess we are live now. So let me just check.
Yeah, we are live.
Okay. So hello everyone, welcome back to channel. और आज हम एक बहुत ही ज़्यादा इम्पोर्टेंट चीज़ के लिए यहाँ पर इकट्ठा हुए हैं. And this is the great Muon G-2 एक्सपेरिमेंट. मेजरमेंट्स के आज रिजल्ट आने वाले हैं. जैसे कि आप स्क्रीन पर देख सकते हैं कि हमने लाइव स्ट्रीम को ऑलरेडी स्टार्ट कर दिया है. अराउंड 4 to 3 मिनट्स में स्टार्ट हो जाएगा. एंड आज हमारे पास एज अ गेस्ट हैं क्षितिज भैया. एंड मोस्ट ऑफ यू ऑलरेडी नो क्षितिज भैया. एंड ऑल्सो वी हैव आनंद भैया. एंड ही इज ऑल्सो स्टार्टिंग हिज चैनल. So round of applause for him, both of them. And yeah, we will going to start that. उसके पहले बस क्षितिज भैया आप एक और अपना थोड़ा सा बता दीजिए कि why we are here, and after that we will wait for them to start.
कॉन्सेप्ट बहुत सिंपल सा है कि लास्ट कई सालों से एक प्रॉब्लम चल रही है. प्रॉब्लम ये चल रही है कि जो क्वांटम मैकेनिक्स है वो प्रिडिक्ट करती है कि मियॉन जैसे जो पार्टिकल्स हैं, जो एलिमेंट्री पार्टिकल्स हैं, जो कि चार्ज्ड होते हैं और जिनका स्पिन होता है, उनकी एक जी वैल्यू होती है. ठीक है, गायरोमैग्नेटिक बोल दें या फिर सिंपल वर्ड्स में बोला जाए कि उनकी एक मैग्नेटिक प्रॉपर्टी होती है, दे एक्ट लाइक मैग्नेट्स, और उसकी वैल्यू 2 के बराबर होनी चाहिए. बट इन रियलिटी वो 2 के बराबर नहीं होती है. नाउ दिस इज नॉट अ प्रॉब्लम कि वो 2 के बराबर नहीं है, बिकॉज वर्चुअल पार्टिकल्स हो गए या फिर टाइनी डिकोरेंस हो गया, बहुत सारे ऐसे रीजंस हैं जिसकी वजह से वो 2 से थोड़ा डेविएट करता है. दैट इज नॉट अ प्रॉब्लम. प्रॉब्लम इज कि 2 से थोड़ा ज्यादा डेविएट करता है. तो हम लोग थोड़ा बहुत डेविएशन, तो इनफैक्ट क्यूएफटी बहुत अच्छे से प्रिडिक्ट कर रही है, लेकिन इतना ज्यादा डेविएशन हो रहा है वो क्यूएफटी प्रिडिक्ट नहीं कर पा रही है. तो एक क्वेश्चन आएगा कि वाई म्यून ओनली, वाई नॉट इलेक्ट्रॉन. और इसका सिंपल सा रीजन है कि म्यून बहुत हैवी होता है, और म्यून हैवी होता है तो उसमें हम लोग ये जो जी फैक्टर है उसको हम लोग उसका जो डेविएशन है वो स्टडी करना कंपेरेटिवली ज़्यादा आसान होता है. नाउ म्यून से भी ज़्यादा हैवी पार्टिकल एक होता है टाउ. टाउ अब देखा जाए आइडियली ज़्यादा बेटर कैंडिडेट है फॉर दिस काइंड ऑफ एक्सपेरिमेंट. बट द रीजन वी डोंट यूज दैट इज बिकॉज टाउ डिकेज टू क्विकली. म्यून भी जल्दी डिके हो जाता है, लेकिन टाउ उससे बहुत ज़्यादा जल्दी डिके हो जाता है. तो वी कैन से कि म्यून इज गिविंग अस अ स्वीट स्पॉट, जहां पर इलेक्ट्रॉन जिसका डिके लाइफ बहुत ही बढ़िया है लेकिन बहुत हल्का है, और टाउ जिसका डिके लाइफ बहुत कम है लेकिन बहुत हैवी है, वहां म्यून हमको दोनों के बीच का एक बैलेंस देता है. एंड बिकॉज हम लोग ये 2 से डेविएशन देख रहे हैं, दैट्स व्हाई वी कॉल इट एज g-2. एंड दिस मीन्स अ लॉट, बट अभी मैं फर्दर बोलते नहीं रहूंगा. वी हैव अनंत आल्सो, सो ही कैन कंट्रीब्यूट फर्दर.
Yeah. Now Anand भैया, please give some
थैंक्स.
words.
आई गेस क्षितिज भैया ने ऑलरेडी बहुत ही ब्रीफ और बहुत अच्छे से कंसाइजली प्रेजेंट कर दिया प्रॉब्लम को. फॉर मी द प्रॉब्लम पर्सनली बिकम्स एक्साइटिंग, क्योंकि जो हमारे पास इलेक्ट्रॉन है तो क्वांटम फील्ड थ्योरी इलेक्ट्रॉन के लिए g-2 से बहुत ही ज्यादा अच्छे से मैच कर जाता है. बट जब हम म्यूऑन की बात करते हैं तो एक बड़ा डेविएशन आ जाता है, एंड दैट इज द मेन प्रॉब्लम. अगर वो इलेक्ट्रॉन से भी डिविएट कर रहा होता तो क्यूएफटी में कुछ इशू होता, बट this just means that the theory might be incomplete. Also, muon is 200 times heavier than the electron, so there might be some virtual particle interactions जो उस muon के साथ take place कर सकते हैं जो इलेक्ट्रॉन के साथ नहीं हो रहे हैं. These might be virtual photons, virtual Higgs boson, or maybe some other virtual particle that has not yet been discovered. So yeah, let's just wait for the results, and उसके बाद we can obviously discuss what the result actually means.
Yeah, so if I say from my side, so I just mention a very brief history of this thing. In 1947, the electron, like discovery of electron as an anomalous magnetic moment, जब हुआ था by Koch and Foley. After that, we get into 1960 and 70s when early muon g-2 experiments at CERN are going on. After that, 1997 to 2001, Brookhaven National Lab में हुआ था E821 एक्सपेरिमेंट दैट फर्स्ट हिंटेड दैट डिस्क्रिपेंसी जो इसके बारे में आज हम बात कर रहे हैं. आफ्टर दैट 2017 से प्रेजेंट काफी सारे एक्सपेरिमेंट हुए दैट इम्प्रूव द एक्सपेरिमेंट यूजिंग द सेम मैग्नेट रिंग बट विथ बेटर प्रिसिजन. सो आज फिर से हम उसी के एक रिजल्ट के बारे में बात कर रहे हैं दैट विल बी अ वेरी ग्रेट थिंग. एंड आई गेस चीजें स्टार्ट होने ही जा रही हैं. So let's just listen into that.
Here we go.
Welcome, everyone. It's a pleasure to see the auditorium full of people like you. I'm so excited to see the new G-2 results. And it's a pleasure to kick us off this morning. Our lab director, Young-Ki Kim, is unavoidably away from the lab this morning, but here on Zoom, and I will let her do the full introduction. So please take it away, Young-Ki.
Thank you, Bonnie. Greetings from Washington, D.C. I'm here for the meetings with congressional members and staff. So as you know, this is a very critical time for all of us for our future funding. So good morning. I thank you all for joining us. And I know some of you are joining from overseas, and so many thanks for those who are watching this joining far, and for staying up, some of you probably very late to hear this exciting news. As Bonnie introduced, I'm Young-Ki Kim, and I'm interim director of Fermilab. Fermilab occupies a unique and vital position within the United States national laboratory system and in the world. And our mission is to explore some of the most fundamental questions in science, questions that delve into the fabric of our world and our universe. At the heart of our research lies the study of the most fundamental units of matter, and among them is the muon. Despite its fleeting existence, the muon holds profound implications for our understanding of the universe. By better understanding the muon, we can gain new insights into the entire subatomic world and cosmos. This knowledge not only enhances our comprehension of the universe underlying principles, but also lays the groundwork for future discoveries that benefit us and help in ways we can scarcely imagine today. Today, we are proud to announce the final results of the Muon G-2 experiment. Through this experiment, we'll have the most precise measurement of the magnetic anomaly of the muon. And this measurement will be a benchmark for many years. The result will help increase our understanding of particle physics that encapsulates our current knowledge of how the universe works at the subatomic level. Beyond my excitement as a Fermilab's interim director, I also have a personal connection to this important experiment. From the inception of the experiment to the groundbreaking of the Muon G-2 building at the lab, I served as a deputy director under then Fermilab director Pierre O'Donnell. So it's even more gratifying to be with you today in my current role to help roll out the final result. In a moment, I will turn to the experiment's spokespeople, Marco Incagli from INFN Pisa in Italy, and Peter Winter from Argonne National Laboratory to tell you more about the results and how these results were obtained. But first, I would like to congratulate and thank Marco, Peter, and the collaboration, and all those who contributed to today's results. That includes Brookhaven National Laboratory and our colleagues who conducted the previous research in this area and supported our work. These results have been years in the making and represent the hard work and dedication of so many people, not just at Fermilab, but around the world. The Muon G-2 collaboration involved 176 scientists from 37 institutions in 7 countries, analyzing 6 years of data. That data was based on trillions of muons produced by the Fermilab accelerator. Well, to be precise, 308.5 muons were analyzed, I was told. I want to take this opportunity to thank our Fermilab accelerator team for their dedication and contributions to this exciting moment. Scientific discovery is rarely the product of a single individual or institution. It is the result of collective effort, diverse perspectives, rigorous analysis, inspirited debate, and shared commitment converging to advance our understanding. At Fermilab, we take pride in fostering such collaborations both nationally and internationally. The success of the Muon G-2 experiment exemplifies what we can achieve together. As we look ahead, Fermilab remains committed to pushing the boundaries of knowledge through ongoing and future projects. Each initiative brings us closer to unraveling the mysteries of our universe. With that, I'll turn it over to Marco and Peter.
Good morning. Welcome everybody for being here. Thanks to Director Yankee Kim for her kind words, and sorry for the small interference that we had at the beginning. So today we will present our final measurement on the hadronic cross-section, on the muon magnetic anomaly, an important quantity that will be described in the next talk. And we can say that this final release ends a journey that started many years ago. And we can say that it was a successful journey. We managed to collect the statistics that we needed, the number of events that we needed to reach our goal. And we reached and even surpassed the reduction of the uncertainty with respect to the previous measurement that was set as our goal in the TDR, the technical design report, 11 years ago. And this is not always the case. And this success is due to some factors. First, ours is an international collaboration with a key role played by US institutions, but with an important contribution from institutions in Europe and in Asia. And the convergence of different scientific cultures on the same project has been an enrichment for all of us, but most of all, it has been an important boost for the experiment. Second, the experiment is really made by the collaboration of communities that normally work on different experiments. In fact, unlike other high-energy physics experiments, the G-2 collaboration is made on top of particle physicists by accelerator physicists, nuclear physicists, atomic physicists, experts in laser theoreticians. And it was very valuable to see that when we had all these experts working together, it was possible to solve problems that a single group could not have been done alone. And this was a benefit not only for the collaboration, but also for the many young and talented collaborators that we had throughout the years. In fact, on top of the numbers that you will see that will remain as a reference for many years to come, this is probably the most important legacy of our experiment, that of having formed a generation of young physicists with many skills and with an open view, with multiple competencies, young physicists that will take this experience into their life, into their societies, and thanks to Fermilab that has allowed for this to happen. Thanks to you for being here. And now I switch to my colleague and co-spokesperson, Peter Winter.
Thank you. It's been quite a journey, as you can see from our timeline. It started back even earlier than
एकदम
2008,
excitement से भर
but
रहे
that
हैं,
was when the
last में
proposal
question
was
mark डाल
submitted.
दिया.
There was the CD0 in 2012, the big move you might have seen, of course, in 2013, and then data taking, and now we're here at the final result, which you will hear later by the next speaker. Just to give you a glimpse, there are many memories and highlights of our almost 2 decades, but we stored more than 1 trillion muons, 200 million times at least. We kicked the kicker and pulsed the kickers and the quads. 6 years of data taking led to more than 50 petabytes on tape. And as Marco said, around 200 collaborators from all around the world wrote a lot of documents on the analysis, and we had 30 plus theses to make this happen. And of course, this doesn't only happen by the collaboration alone. We really thank also the host lab, Fermilab management, the engineers, technicians, operators that may help us construct, design, and operate the experiment, the administrative staff, not only at Fermilab, but everywhere in the institutions that run behind the scenes all the processes, and also our communications teams that disseminate this result today in our on our behalf. And of course, at the end, we would like to say thank you to the funding agencies all across the globe. But of course, we would very much also highlight a few from the U.S. funding agencies that have accompanied this experiment throughout the project phase and through many reviews, advice, and of course, the priorities in funding for us to make this happen. Thank you so much. And with that, I'm really happy to hand it over to Simon, who will give you the scientific results.
Thanks a lot. I'm Simon. I'm one of the Muon g-2 co-analysis coordinator, and it's really my honor to present you here the final g-2 results from the Muon g-2 experiment at Fermilab. So let's directly jump into what is this G that I have twice in my title. G refers to the G factor, which is a quantity that connects the spin of a particle, which is an intrinsic property with its magnetic momentum shown here. So what does this really mean? If I take now such a particle, the blue one here, it has this intrinsic property that we call the spin, indicated with the black arrow. If we place this particle now in a magnetic field, shown with a green arrow here, the spin of this particle starts to precess around the magnetic field. Now the speed or the frequency with which this spin precesses is determined from the magnetic size of the magnetic field we place the particle in and this G factor shown here. So this G factor or G factors has been a very, very important quantity in the history of physics. In classical world, where we just would consider a simple current loop, G would be 1. But then pretty early on, the Stern-Gerlach experiment and others found actually that the G factor of the electrons was not 1, it was closer to 2. This brings us into a quantum world where we have a Dirac theory. For a Dirac spin 1/2 particle, G is actually 2. And we often indicate this with a diagram that looks like the one displayed over here. So, but soon after this formulation of this theory, experiments actually found that G was slightly larger than 2 and not only 2. This brings us to the really famous Schwinger prediction that Schwinger predicted a correction to G of the form alpha over pi. We indicate this with the diagrams that look like this. So Schwinger's the underlying idea of Schwinger's prediction is that we have virtual particles that alter G. So we have particles that can pop out of the vacuum, interact, and disappear again. And while doing so, they actually change the value of G. So there's really this idea that led to the foundation of the standard model of particle physics as we have it today. So what is the standard model? The standard model, and we often display it like in the family tree over here, it encodes all the particles and all the interactions that we know today. And as I mentioned before, interactions with virtual particles alter G. And it turns out that all particles and all forces in the standard model actually contribute to the value of G. I would like to walk you through the different contributions. We have the Dirac term. This is where the 2 comes from. Then we have QED contributions, where I already showed you the famous Schwinger correction. Then we have QCD corrections, hadronic vacuum polarization, and hadronic light by light, and there's contributions from the electroweak forces. Now, I really would like to highlight here the hadronic vacuum polarization, because this is going to be really important afterwards in the story. So while the standard model is incredibly successful framework to describe everything we know, there are clearly questions that the standard model does not answer. For example, one of these questions is, why is the universe that we see, that we can touch, made out of matter and not of antimatter? So from this, we know the standard model is not complete. There has to be more. There has to be more particle or forces somewhere. And the question that arises now is, do these additional particles and forces also contribute to G, indicated with this question mark? So we know that these particles must exist, but we don't know what they are. So in the beginning, I mentioned that it's muon G-2. So we use muons, but what are muons and why are we using them? Muons are second generation charged leptons. If you look at our family trees, they live over here. They are just like electrons, but they are 200 times more heavy. And this is the fact that they are 200 times more heavy, which makes them more sensitive to these virtual particles, to these contributions that I mentioned before. Muons are not stable, they decay. Muons decay into an electron together with neutrinos. But in our experiment, we typically don't see the neutrinos. This decay is parity violating. That means it has a quantity that I would like to call self-analyzing here. The electrons, they preferably decay into the direction of the muon's spin. So that means, in other words, that information about the spin of the muons is encoded in the electrons. Okay, so what do we really measure in our experiment, right? Sure, we measure G-2, but why do we do this? We do this because we want to test the standard model. Here, I display the different contributions to G-2 I mentioned before. In the hashed areas, this is the uncertainties that we have today from calculation. I add these particles that potentially new and we don't know about here in the graph. Now, over the years, there have been many G-2 experiments, increasing precision experiment after experiment. So each generation of these experiments probed smaller and smaller physics contribution to G-2. So all these experiments, G-2, what we're really trying to answer is the question whether there's new particle or forces that show up in our experiments, but they don't show up in the calculation of the standard model, the blue contributions I show over here. So this brings us to our experiment, the Fermilab G-2 experiment. The experiment we set out to measure G-2 with a precision of 140 ppb. But what does this really mean, 140 ppb? So ppb, these are parts per billions. So a 140 ppb measurement is a measurement with 8 significant digits. Or in other words, if we would try to measure the weight of a bison here at Fermilab to 140 ppb, this would allow us to answer the question whether someone has added a sunflower seed to the bison or not. Okay, but how do we do this? So the principle is that we store polarized muons, and I indicate the muon here with the arrow. And these polarized muons, we place them in a strong dipole magnetic field. The magnetic field, again, indicated with the green arrows. Now we have a muon in a magnetic field, then it circles around, and we can store them. The frequency with which the muon goes around, we call this typically the cyclotron frequency, shown with the formula. Now I said polarized muons. What does this really mean? Polarized muons means that the spin of the muons have a defined direction. If we are now in a world where G would be exactly 2, that means that the formula of the spin precession I presented you before would cancel out. It would exactly be this. This term would be 1. It would be exactly the same as the cyclotron frequency. So over time, in such a world, there would be no phase difference be building up between the spin and the momentum of the particle. But now we know we live in a world where G is actually larger than 2. That means the spin precession is actually larger than the cyclotron frequency, the momentum rotation. So if I play this in our world, the spin actually rotates faster than the momentum. So over time, there's a phase difference building up between the spin and the momentum. And it's this phase difference the phase build up is a frequency that we measure and we typically call omega A. It's a spin precession frequency of the muons. I'm going to focus more on the formula in the center on the next slide. So typically what we do, we call G-2 the magnetic anomaly, and we call it with the formula sign A mu to make our formulas a little smaller. So what we do, we measure G-2, this magnetic anomaly A mu. This is what we want to extract. And in order to be able to do this, we need to measure two things. We need to measure the spin precession of the muons, omega A, I showed you before, and we need to measure the magnetic field in which the muons live. So we have been doing this for quite a while. We have been taking physics data for over 6 years in chunks that we call runs. The first physics data was taken in 2018, and we call this run 1, which result we published in 2021. This was followed by run 2 and 3, which together is 4.6 times more data, more statistics than run 1 had. So this is the situation before today, where today we're going to talk about run 4, 5, 6 afterwards. So how is the situation before we came into today? What I show you here is the result from the Brookhaven experiment, our predecessor experiment displayed in blue. At the same time as our experiment formed, the Muon g-2 theory initiative also formed. The Muon g-2 theory initiative is a consortium of more than 100 theorists that compile the theoretical input and make recommendation for the calculation for g-2 in the standard model. Before our publication, they published a white paper, the white paper 2020, which value I display in green. And it's this discrepancy between the experimental value over here and the theoretical calculation in the standard model over here that also motivated our experiment. So there's one important point I would like to make for this white paper 2020. One of the components, the leading order hadronic vacuum polarization, and here it is again, the hadronic vacuum polarization I was mentioning before, is calculated in a data-driven way. They use experimental cross-section data from different experiments that span more than 20 years. I list the experiments that go into the white paper combination in the figure over here. The individual plots here correspond to where the g-2 calculation would show up if only data from one of these experiments would be used. This brings us out to our run 1 publication. Our run 1 publication was in very good agreement with the Brookhaven result, further increasing this discrepancy between the experimental average at the time and the white paper 2020 calculation. At the same time as we published our run 1, the BMW collaboration published a calculation of g-2 that uses a different method to calculate this leading order hadronic vacuum polarization. And this publication was the first high precision calculation using a method called lattice QCD. Lattice QCD is a computational method that doesn't rely on experimental input data. I show you the value from this publication in orange in the lower part of my plot. And you can see the calculation from lattice is in tension with the calculation from the data-driven approach by paper 2020, and the tension with respect to the experiment is largely reduced. Soon after this, there was a new experimental cross-section measurements became available that were not included in the white paper 2020. And most notably, the CMD3 cross-section measurements are in significant tension with the cross-section measurements that are used in the calculation for white paper 2020. Our run 2-3 result reduced the uncertainty on the experimental average by more than a factor over 2, increasing the tension between experimental value and white paper 2020 calculation significantly, but then there's no real tension with respect to the lattice calculation, and there is no real tension if we would only use the CMD3 cross-section measurements for the calculation. This brings us to just last week, where the theory initiative published an updated white paper. It's their white paper 2025. Different than before, in this recommendation for this leading order hadronic vacuum polarization, now only lattice QCD inputs are used. That's the reason I showed the white paper 2025 value in orange in the lower part of this plot. This combination here is compiled from several now published QCD calculations. The white paper is an archive, and you can find all the details on the link here. Okay, with this, now I would really like to focus on the experimental side, on our result, and the question, where does our run 456 result land on this plot over here? So, how do we do? I mentioned, we have run 456 now. That is 2.6 times more data than we had run in run 1 to run 3. So how do we do, and how do we actually measure this? So first of all, we are at Fermilab. Today, we are in the auditorium. Our experiment is located in a building called MC1, which is highlighted in orange over here. At MC1, we get muons at 3.1 GeV. This is what we call the magic momentum, and I will tell you afterwards why we call it the magic momentum. We get the muons from pion decays that we get from 8 GeV protons from Fermilab's main injector. Then once at MC1, that's how it looks like, our experiment. The core piece is our large storage ring. That it's the same storage ring that was already used in the Brookhaven experiment. The storage ring is a superconducting magnet, produces a strong 1.45 Tesla magnetic field that we need to store the muons. It's designed and optimized further for homogeneity. So the coils that are in the cross-section over here, the coil of the magnet are indicated with yellow, and they produce the strong magnetic field where the muons are stored here that I showed you before that we need to store the muons. So now that we get muons from the accelerator complex, we inject them through a field-free injection channel, and they enter with an offset in our experiment. If we would do nothing, they would just curl around and leave the ring again on the other side. So we need two systems to actually store them. The first one is what we call a kicker. In the first round, we need to kick the muons a little bit to bring them onto storage orbit. This is how our kicker plates look like. So with these plates, through which large currents flow, producing an additional magnetic field in the center here, changing the trajectory from what you see here to a storage trajectory. However, if you would do nothing, now the muons would just leave going upwards or downwards. So we have a second system to confine them in this direction. This system is called the electrostatic quadrupole plates. They look like this. They span more than 50% of our ring, and they produce a strong electric field that we use for vertical focusing to get the muons focused inside our storage ring. There's something new in run 5 and 6. It's what we call an additional RF modulation. So typically, we run these electrostatic quadrupole plates with a high voltage of 18 kilovolt over here for the duration of 700 microseconds, the time we actually store muons. But new, the addition is that on top of some of our plates, we have this small 1 kilovolt modulation that looks like this for the first roughly 6 microseconds. And the idea of this modulation is to influence the beam dynamics, as I will describe later on. Okay, now we are able to store muons. We store several thousand muons at a time. The boosted lifetime of the muons, because we get them at 3.1 GeV, is 64 microseconds. And as mentioned before, we store them for up to 700 microseconds. So really, we store them until all of them are decayed. Speaking of decay, our actually positive charged muons decay into positrons. And since the positron momentum is smaller, they curl inward like this. Now we have two main sets of detector to detect these positrons. The first one is our calorimeters. We have 24 calorimeters that are equally spaced around the ring, indicated in the location highlighted in green. And these Cherenkov lead fluoride crystals look like this and detect the energy of the positrons and the precise arrival time. In addition, we have a laser system that helps us to monitor and calibrate the gain of this system. The second set of detectors we have are our trackers. We have two tracker stations at the red highlighted areas. The trackers reconstruct the positron tracks, which allows us then to reconstruct the muon decay vertex, which then allows us to actually reconstruct the muon distribution inside the ring. And I would like to focus on this muon distribution for a moment. So here, the muon distribution inside the ring plays as a function of time as it goes further on. And what I like to really highlight is this motion. You see that our muon distribution is radially moving inwards and outwards. And especially the mean of the distribution, which is displayed at the bottom, you can see that we have this strong oscillation. It's this oscillation that we call coherent Betatron oscillation, CBO. So before I mentioned that we have this new RF system, what I show you here is without this RF system. But now we installed this RF system, and the muon distribution looks like this. And especially if you look at the projection of the mean of the distribution at the bottom plot, you see that this RF system significantly reduces this CBO, this oscillation of our beam, of the mean distribution. So how does this really work? This RF system, it's displayed in this sketch here. The RF system acts like a forced harmonic oscillator, but only for a really short time of 6 microseconds in the beginning. If we tune it right to the CBO frequency and the right phase, indicated over here, we manage to phase shift different muon distributions differently, which results in a reduction of the oscillation of the mean of our distribution. Okay. Actually, it turns out that we use these RF system conditions to split our data set. So our 1456 data set is split into 4 data sets. We call it no RF, which is a data set where no RF system is present. This is mainly run 4. We call it XRF. This is the data set where this RF system is present in the horizontal plane. And we have 2 data sets, XYRF, where we have the RF system present in the horizontal and vertical plane. With this, I would like to come back to the question, how do we actually measure omega A, the spin precession of the muons that I mentioned before? And we do this with our calorimeters. What I show you here is an energy spectrum of the detected positrons of one of these calorimeters. And you can see it modulates over time. This is from the self-analyzing property of the muon decay. So it turns out that high energy positrons, we get more high energy positrons whenever the spin of the particle is aligned with its momentum, and then when the spin rotates, we get smaller. So the question is, how do we actually extract this frequency omega A from this varying momentum spectrum? And what we do in our experiment, we count the number of positrons above a certain threshold indicated with the orange area over here, or we weight them by the asymmetry. So if we now count the number of high energy positrons as a function of time, we get this distribution and we get this modulation on top of it. And this modulation corresponds to the spin precession frequency omega A that we want to extract from our data. So how does this data really look like? What you see here is one of our famous wiggle plots. In this plot, this is the full data set from run 456, and typically we wrap them around here at 100 microseconds, so it actually fits onto one graph. There's 2 distinct features you can see. Overall, we have the muon decay here, and then on top we have this modulation I already mentioned, the modulation on top, which is exactly this omega A that we want to extract. So if we would just take a simple model like this that has these 2 main features and fit it, we get residuals, and then we can look at the frequency spectrum of the residuals. And this is how the frequency spectrum would look like. So there's all these peaks going on. And all these features in the frequency spectrum of the residuals are due to beam dynamics that I mentioned before. The CBO I mentioned before is the most dominant one, which you can see again right over here. So in reality, we need to account for beam oscillation, muon losses, and detector effects. And once we do this, our frequency spectrum of the residuals turns from the blue to the red one, and it's completely flat. There's no feature left. It really shows how well we understand the beam dynamics in this experiment. There's one example I would like to make. I would like to come back to this CBO, the beam dynamics I showed you before. If we were not to account for this effect in the fit function, then our result would be shifted by 800 ppb. And just remember, we want to measure omega A, we want to measure g-2 at the 140 ppb level. So no worries, we do account for it, but it's impressive to highlight. However, if you have now a data set where the RF is present, the same effect reduces by a factor of 10 to 80 ppb. So overall, really this large size of the run 456 data set allowed us to split the data set and really also demonstrate consistency between what I would call largely different running conditions. Okay, time to recap a little. We want to measure a mu, and I started to display how we measure omega A to do this. Sorry, we want to extract a mu, and I started to explain how we measure omega A. So this formula is it's simplified. In reality, there's additional terms. We have a term in the center that mainly cancels almost out because we are in a storage ring. But we have a second term on the right side that has beta over here. Beta is the direction vector of our muons and the electric field. And it turns out, as I mentioned before, we really do have electric field from the electrostatic quadrupole plates that I mentioned before. So this term doesn't cancel out. But what we do, we adopt the method of running at the magic momentum. So we get muons, we use muons, at roughly 3.1 GeV, which yields a gamma factor of our muons of 29.3. So this is really tuned so that the factor over here cancels out. So this, if we have now muons on the magic momentum, then there's no correction needed from this part. And this is why we call it the magic momentum. It's because of this cancellation. However, you can imagine not all muons have exactly the same momentum. So that means for the muons that are off magic momentum, there is a correction. And we have three, for this correction, the main ingredient is really to understand our momentum distribution. And we have different methods to do this. We can do this parasitically. We can use tracker data and what we call the dispersion. So we can exploit the fact that higher momentum muons live actually at larger radius and beam dynamics. We can also use our calorimeters, where we exploit the fact that since the larger momentum muons live at larger radius, they have further way to travel than the lower momentum muons. So that means that the different muons dephase over time. And now, new in run 456, we have an additional detector that's pictured here. It's a minimally intrusive scintillating fiber detector, the mini sci-fi. We have a vertical and a horizontal version of it, and we inserted it for a dedicated run. It's not a parasitic measurement, really to cross-check these measurements. So putting these pieces together, we can extract our momentum spectrum that I show you here, again, for the different data sets. The 0 here means it's exactly on the magic momentum. So the muons that live at 0 don't need correction, and everything outside of this all the muons outside contribute to the correction. And again, I listed this for the different data sets that I was mentioning before, and you see that the RF helped us to actually center the momentum distribution a little better. With this, we have all the ingredients to extract this electric field correction that I mentioned before. This is our largest correction. In this figure here, you see on the x-axis our sub-data sets. Then the different colors are the different methods I mentioned before. And you see that the different methods agree very well within our uncertainty, total uncertainty that we assign, which is the gray bar. So this is the electric field correction. This is our largest correction, but there's other corrections we need to make. Another one that comes from beam dynamics is what we call the pitch. This is from the fact that the muons go up and down from oscillations. It's smaller than the electric field on the size of 170 ppb for run 456. In addition to these corrections that come from pure beam dynamics, we have an other set of corrections highlighted in green, but the amplitude of them is much smaller. All these green corrections arise from the fact that the mean phase of our muon ensemble changes over time. And whenever we have a phase change over time, that corresponds to a frequency, and this biases our fit that we need to correct for. Okay, now I want to recap a little. So we want to extract a mu. I hope I convinced you that we know how to measure the spin precession of the muons, omega A. Now the second ingredient we need is the magnetic field, B, over here. And we measure B by using the gyromagnetic ratio of shielded protons. So what we really measure is we measure the precession frequency of protons in the same field as the muons live. However, the catch is we cannot place the muons where we cannot place the protons where the muons are because we need vacuum to actually store the muons. So what we do in reality, we make field maps, and we map the field in 3D, and then we weight the field maps with the distribution from the muons. And then in addition, there's a correction term similar to omega A that I will talk about afterwards. So how do we really do this? Sorry, but I should say then once we have this, we can put parts together, so we can express A mu as a ratio of our two measurements, omega A, I talked before, and what we call omega P tilde prime, the measurement of the magnetic field through the protons, together with external components that I will detail afterwards. With this, I would like to show you how we actually measure the magnetic field. We do this with a nuclear magnetic resonance, and you can see a petroleum-based NMR probe in this picture. Where we have fixed installed NMR probes above and below our storage volume that track the field all the time. Then inside our volume, we have the trolley, a field mapper that has 17 of these NMR probes and can be deployed into the ring and is pulled around the ring in 70 minutes to map the field in 9,000 2D slices shown in the sketch over here. So now we map the field every 3 to 7 days, and in between we track the field with the fixed probes I showed you before. So now we get a measurement of the magnetic field as seen by these trolley probes. However, these NMR probes that sit in our trolley inside here, they not only see the external magnetic field, they also see the magnetic field, the environment from the trolley itself. So we need a calibration. And as mentioned before, we calibrate with respect to shielded protons in a ferricon sample. We do this with our water-based cylindrical calibration probe shown here. This probe is really designed to minimize all material effects, so we can measure them, correct them, and is very well understood. So the actual calibration is now a two-stage process. We have an in situ part, where before and after each run, we calibrate our NMR probes in the trolley with respect to this water-based cylindrical probe. And in a second step, we correct for material effects and the sample shape, really bringing us to the shielded protons in a spherical sample, which we typically indicate with the prime over here. Since this is a very crucial step, we have cross-calibrations. We cross-calibrate our calibration probe against other magnetometers. We have field maps. The missing part is the weighting with the muon distribution. That's in this figure. We get the muon distribution at 2 locations in the ring from our trackers. And then we have dedicated different simulation frameworks that allow us to propagate these measured muon distributions around the ring. In this figure, you see the azimuthally averaged muon distribution in the color scheme with the contour lines. So this is where the muons live inside our storage ring. And then on top, you see the azimuthally averaged magnetic field with the white contour lines. As mentioned before, also on the field side, there are corrections like I showed for omega A. We have 2 of them, and they both are due to transient magnetic fields. So transient magnetic fields, these are effects that are synchronous to our beam injection, muon injection, but they are not part of our NMR system because the NMR system runs asynchronously. We have 2. One we call BK, which is from the kicker. I'm going to talk about this in the next slide. And we have a smaller one, and that is we call BQ, that arises from vibrations in our ESQ slides. So if we go back to our kickers, the strong kick in our kickers causes eddy currents in the vacuum chambers and the plates itself. And it's these eddy currents that cause transient magnetic fields. Now, newly in run 456, we have 2 different magnetometers that we use to measure these. You have the pictures. Here is the blue legend, and we have a fiber magnetometer where you see an optical fiber bringing in the light into the center of the kickers. What I should have mentioned before is that both of these magnetometers use a Faraday effective TTG crystals. So the crystal sits inside here. Then we have a second magnetometer, which is a free laser magnetometer with the red legend over here. The laser goes through a window, and we use mirrors here to guide the light into the center of the kicker plates. The measurement is shown over here. The corresponding curves match the color matching over here. And the first thing you can observe is that the color matching, that the 2 measurements at the same location agree very well with each other. Then if you focus on the x-axis, on the time axis, but the time we really care about is the time that we use the muons for our fits, which is indicated here with these bars. Focusing on the y-axis, you can see that it's a milligauss measurement on top of a kick that has 220 gauss. So the dynamic range of this measurement is truly astonishing. And lastly, I indicated the range here in terms of our main field. So this here corresponds to 1000 ppb. However, the effect is averaged over time and space, and in total, it comes down to 30 ppb effect. Okay, with this, I would like to kind of summarize and play this while I'm talking. So I mentioned before we have this trolley, and this is the view from the trolley and on our experiment. So what we did, we mounted a camera in front of the trolley, and it goes once around the ring. Now here, we just passed the injection. What you see here are these electrostatic quadrupole plates inside our ring. Now we are 90 degrees inside our ring, which you can see the kicker plates. We're kind of speeding up. I mentioned before it takes 70 minutes for the trolley to go once around the ring. And here, down here, you see the speed that we speeded it up so that it doesn't take so long here. And over here is the garage where this trolley is parked. Then just behind the trolley garage is this calibration probe that we use for the in situ calibration. It's shown over here. The next part you're going to see is one of the tracker stations. There's more quadrupole plates because they span 50% of our ring. The next thing you're going to see is a collimator that I've not talked about it, but it looks really beautiful, so I thought to show it here. We need to flip up this collimator so the field mapper can actually go through. So now we have covered 3/4 of the ring, and we speed it up, and the last quarter looks basically the same as before, another tracker station. Now we are once around the ring, almost. Okay, with this, I'd like to recap. We are talking about run 456. We have 2.6 times more statistics than before. Where does this bring us? What we have is an overview of all contributions, and we have our ratio of measurements with the corrections. There's a few things I would like to highlight here. So first of all, our largest correction, the electric field correction that we already talked about. Then the statistics of the run 456 is 114 BPB. This mainly comes out of the number of observed positrons. Then if I focus on the systematics, these are the same numbers, just differently displayed. First of all, our total comes to 76 ppb, clearly succeeding our TDR goal of 100 ppb systematics. And secondly, the systematics are really evenly distributed, or roughly evenly distributed between the different categories. To calculate now G-2, we also need these external constants that I mentioned before, and we have two of them. The first one is the ratio of the shielded protons, the ratio of shielded proton magnetic moment with respect to the Bohr magneton, which is known now on a 4 ppb level, and we have the mass ratio between muons and electrons, which is known on the 22 ppb level. So all this together allows us to arrive at our final uncertainty of 139 ppb, which run 456 alone matches our TDR goal of a 140 ppb measurement. Before I show you where we end up, I would really like to highlight this incredibly team that really is needed for this kind of analysis. What you see here is a picture from 2 weeks ago at our unblinding event. Our collaboration has at the moment 176 collaborators from 34 institutes from 7 different countries. And it's really important to highlight that our collaboration spans a huge variety from physicists and engineers from different fields I tried to list over here. And it is really this diverse team from different disciplines that we need, because this is a very, very complex analysis. So just to highlight this, I show you here our top-level documentation for the run 456 analysis. And you can see it's it's a lot of documents, and it's very deep. I cannot go into all the details today, but after my talk, you can find our paper here, or later on archive, or then we will submit it to PRL and will be published there. So, recapping run 456 a little. Run 456 has really superior statistics. We had additional measurements, and we had additional simulation efforts that really allowed us to cross-check many things and get some new insights. Before now, we can combine our run 456 results with run 123, and we applied some of the new knowledge from run 456 also to run 123. And there's a few corrections we made. I don't want to go into details. I just like to flash them here briefly. First of all, we identified a new intensity-dependent gain sag. Then we improved the spatial modeling of the kicker transient that I showed you before. And lastly, unfortunately, we identified and corrected a sign error of a subcomponent of one of the smaller contributions I showed you before, with the size of 12 to 20 ppb. All these corrections go the same sign. In total, this is a correction of almost 100 ppb. So with this, we are in a position where we compare our run 1, run 2, 3, and run 4, 5, 6. This is what I show you here, and then run 1 to 6 is the combination of everything. The first column is the number of analyzed positrons. I already showed this in the graph before. Second column is the fraction of the total data set, and then at the end here is the statistical uncertainty. And what I would like to highlight that the combined run 1 to 6, we have a statistical uncertainty of 98%, which clearly matches our TDR goal. Now, if you look at the uncertainties overall, I already talked about the statistics. I introduced the systematics. And if you compare the systematics between run 456 and run 23, first of all, you can really see it's on the same order of magnitude. So this run 456 really stands on the shoulder of all the work that was already done in run 23. And secondly, we really seem to have reached a bottom of what's possible with this method. And then lastly, I would like to highlight our total uncertainty of 125 that clearly matches CDR goal. The last thing I would like to mention on this slide is that our result is still slightly statistics dominated. Okay, with this, we are almost ready to answer the question, where will run 456 end up on this plot? Before I do this, I would like to mention that our analysis is software and hardware blinded, where here I really want to focus on the hardware blind. A hardware blind means that we alter our clock that we use to digitize our signals by 40 megahertz minus a delta over here. And this delta is not known to the collaboration at all until the vote for unblinding until we vote for unblinding, and then we reveal the true value. This means there's really no way we can know where it ends up. Speaking of unblinding, we unblinded our results 2 weeks ago, and you can see Peter, our spokesperson Peter, and Marco here at Fermilab 2 weeks ago, opening the sealed envelopes, really revealing this unblinding number. So now, where will run 456 end up? Run 456, shown here, is in excellent agreement with our 1, 2, 3, and previous. It reduces the uncertainty with respect to run 1, 2, 3 by a factor of 1.8. If we combine the full Fermilab data set, we increase the precision, we decrease the uncertainty with respect to Brookhaven by over a factor of 4. And if you look at the experimental average that is shown over here, that is now the experimental average is completely dominated by our experiment, increasing by a factor more than 4 with respect to Brookhaven. And one part that I would like to show you, and this is really a common theme to some extent, is these consistency checks. I showed you already the data or talked about the run 456 data, which is shown here in red. So this NoRF to XYRF, these are the run 456 data sets. I also show here our 3 data sets that we had in run 2, 3, our 4 data sets that we had in run 1, and then the 3 data sets from Brookhaven. And this is just an explanation for how consistent our results are, and how we can show and we can use this large data set to demonstrate this consistency. Summarizing, if we compare the experimental value with the theory prediction at the moment, the situation is nuanced, as I mentioned before. Our new measurement and the combined Fermilab measurement is the most precise determination of A mu for many years to come. This 127 ppb measurement tests all contributions from the standard model to g-2. In addition to this, it's really a benchmark for any new models in future, for new particles or forces, for any BSM physics. This is not the end. There's more to come. From our side, we expect also a Muon EDM result, and we have additional beyond standard model analysis ongoing. We have CPT Lorentz violating analysis and the dark matter analysis. There's also more from others. We expect the JPark g-2 EDM experiment plans to take data in the next years. They use a completely complementary technique. And there's also going to be updates from the theory community, including experimental input from data-driven hadronic vacuum polarization, including the Muon E experiment. With this, I would really like to take the opportunity to say thank you. Our collaboration would really like to thank everyone who helped to make this experiment success story. Thanks a lot.
Wonderful.
Thanks a lot. I think we're happy to take questions.
We would invite people to come to the microphones in the front. I will also be in the back, but for questions, it might be the easiest if you come to the microphones.
So basically to sum it up, जो हम लोग desired result चाह रहे थे, वो डिजायर्ड रिजल्ट की तरफ हम लोगों ने अनसर्टेनिटी और कम कर ली है, which is a very good
Nobody's
sign.
getting up, then I will come to you.
Congratulations on a great result and having achieved all the goals you've set out for this measurement program. The thing that stands out to me, and I apologize that it's sort of adjacent to your talk, is that we are now dominated by theoretical uncertainties. And so the question is, what are the prospects for shrinking the uncertainties on the theoretical prediction down to the same level as you were able to achieve on the experimental side?
Yeah, it's clearly a question for the theory community. I can flash this again. I can clearly flash this again. Right, so the white paper 2025 is really a snapshot in time, and it is the timing, I think, was motivated by the fact that we are publishing our results. So there's clearly still work ongoing, and there's potential. And then if you look at the experiments, there's clearly a tension between, there's a cluster over here, we have CMD3, which results over here, that really needs to be resolved in the next years. And then I think in addition, there is going to be a prospect of Muon E, which is going to add another input for this part of the plot.
Thank you for a very nice talk, and congratulations for successful operations and fantastic results. My question is, so how much more budget would you need it if you run mu minus decay instead of mu plus? How much more budget would you have needed if you run mu minus decay for measuring G minus 2?
So, I don't think it's purely a budget question. So at some point there was consideration whether we would our run 6 would be mu minus, and so in a sense it's not much more budget from our side. I mean, we could have done it, but decided we could have done it, but then it's more a coordination with the rest of the Fermilab accelerator complex. I think that it's complicated. So it's not only money-wise; it's really how the program fits into the Fermilab environment.
Okay. So
Congratulations on a beautiful result, beautiful talk. Maybe you can say, I'm sure it's been very
okay. So I just paused it because उनका question session चल रहा है. So we have also some questions from audience in the chat. So let us just take that questions and let's discuss about जो भी result आया है, जो कि हम सब इतना ज़्यादा expect कर रहे थे, but yeah, uncertainty कम हो गई है, and here the result. So पहले question है, let's just take that question on the screen. क्षितिज भैया, आनंद भैया.
श्योर, मैं साथ साथ में एक्चुअली वो जो पेपर उन्होंने रिलीज किया वो भी सर्च करता जा रहा हूँ.
अच्छा, आर्काइव पे. ओके. हाँ, फॉर ऑडियंस जो आर्काइव का कोड है वो मैं अभी पिन कर दे रहा हूँ. आप उसे जाकर पेपर पढ़ सकते हैं इफ यू वांट. बाकी ये क्वेश्चन है, आनंद भैया, क्षितिज भैया, क्वेश्चन देखिए. सो द क्वेश्चन इज, how do you believe that they accounted? Well, first of all, thank you very much, Mayul, for asking the question, for being so interactive in the session, and for joining us. By the way, Mayul Bhaiya is also one of my senior, and he's in Germany for his master's right now. And yeah, his question is, how do you believe that they accounted for the hadron vacuum polarization factor? Okay, so Kshitij Bhaiya, your say on it.
आई डोंट थिंक कि अब मुझे इतना ज़्यादा आइडिया है इस बारे में भी, बिकॉज ये तो प्योर एक्सपेरिमेंटल साइड चला गया.
हाँ, ये बेसिकली
तो पूरा डिटेक्टर कैसे वर्क कर रहा है उसके ऊपर हो गया, फुल एक्सपेरिमेंटल हो गया.
या बट आई गेस अपने प्रेजेंटेशन में बहुत अच्छे से फर्मिलैब वालों ने दिखाया था कि हाउ दे अकाउंटेड फॉर ऑल द different interactions, and वहाँ पे I remember they put a particular emphasis on hadron vacuum polarization factor.
Yeah, and हेड्रॉन वैक्यूम पोलराइजेशन फैक्टर के बारे में आई ऑल्सो डोंट हैव मच इन्फॉर्मेशन, बट जितना मुझे लगता है लाइक इट्स समथिंग अबाउट क्वार्क एंटी क्वार्क पेयर दैट अपीयर ओवर देयर। सो या, और उन्होंने काफ़ी अच्छी तरीके से उन चीज़ों को किया भी था। एंड थैंक यू वेरी मच फॉर एवरीवन जो लोग इतनी देर से थे। एंड वी हैव ऑलमोस्ट 10+ व्यूअर्स all over the time. So thank you very much for all to join. And yeah, at last, what are you thinking? Like उन्होंने भी कुछ कुछ चीजें बताई हैं, like what are they think over it कि वो आगे क्या सोचेंगे क्या नहीं। like dark matter वाला फैक्टर भी है लास्ट में, but I don't think हम उस डायरेक्शन में जाएंगे। What do you
ओके, आई
both?
फाउंड द पेपर।
Okay,
मैं एक्चुअली कब से पेपर ही देख रहा था, मेरा पूरा ध्यान उधर ही था।
okay, let me just put the archive वाला। Okay, 2505 21476।
मैं लिंक भेज देता हूँ ना, डाल देता हूँ।
हाँ, लिंक ही भेज दीजिए, मैं डाल दूँगा।
Me also check.
If anyone has any more questions, please ask in the chat.
आई थिंक ये ऐसा टाइम है कि हम लोगों को भी एक बार अपना टाइम देके एक बार पेपर के रिजल्ट्स देख लेने
हाँ,
चाहिए, एंड जस्ट टू बी
obvi-
क्लैरिफाई कि क्या सीन है।
yeah, obviously. And I am hoping कि आप भी इसके ऊपर कल या परसों भर में वीडियो डालेंगे।
हाँ श्योर श्योर, उसी लिए मैं देखना भी चाह रहा हूँ कि एग्जैक्टली क्या रिजल्ट है।
या मुझे भी डालनी है, तो ये पेपर तो देखना ही पड़ेगा ऑब्वियसली, ये चीज़ें
श्योर।
समझ में नहीं आएंगी। ओके, एक क्वेश्चन और फ्रॉम प्रयोग। So now that we know that standard model is in extreme precision with experimental observation, so what is the drive for going beyond standard model?
सो जैसा कि इन लोगों ने अपने प्रेजेंटेशन में एंड में ही बताया था कि अब इनका जो फ्यूचर वर्क होगा वो थोड़ा इसी साइड ज़्यादा होगा, थियोरेटिकल साइड ज़्यादा होगा, जो कि इनके एक्सपेरिमेंटल ऑब्जर्वेशन से अलाइन कर पाए। तो डार्क मैटर साइड दे वर सेइंग दैट दे आर गोइंग टू डाइव डीपर। और बीएसएम जो है, बीएसएम इज ऑलरेडी, बीएसएम मींस फिजिक्स बियॉन्ड स्टैंडर्ड मॉडल, इट्स ऑलरेडी अ वेरी बिग वेंचर। तो उस साइड थियोरेटिकल वर्क अब बहुत ज़्यादा होने के चांसेस हैं। चांसेस क्या होंगे ही।
Yeah, and
And
also
we also, yeah, बोलिए बोलिए।
मतलब जैसा हम स्क्रीन पे अर्जुन अभी विजिबल है ही कि इसमें हमारे दो अलग अलग अप्रोचेस थे। एक क्वांटम इलेक्ट्रोडायनेमिक के अप्रोचेस थे जो सारे ग्रीन कलर में कोडेड है ऑन द स्क्रीन, बट देयर वाज आल्सो दिस न्यू अप्रोच जो एक्चुअली लैटिस क्यूसीडी को यूज करता है। ऑल्दो लैटिस क्यूसीडी is not very rigorous at this point, जो ये अप्रोच था। एंड दिस वीडियो आल्सो दे टोल्ड कि अभी 2025 का उनका रिसेंट ही पेपर है, एंड they themselves will wait for further development because lattice QCD is a very computationally intensive model. So yeah, प्रयोग के क्वेश्चन में we would also say कि experimentally हम अगर इतने stringent हो गए तो the next step is obviously theoretical, and I do see some promising hope from the lattice QCD part in the future.
Yeah, and also I want to add up it कि अब इससे हमें ये तो पता चल गया है कि स्टैंडर्ड मॉडल इज इनकम्प्लीट बट नॉट रॉन्ग। एंड इवन विथ इट्स प्रिसिजन वी कैन ऑल्सो लाइक जो डार्क मैटर वाला पार्ट है, लाइक 85% ऑफ द मैटर बना हुआ है, बट स्टैंडर्ड मॉडल हैज स्टिल नो कैंडिडेट पार्टिकल फॉर डार्क मैटर। तो या वी विल सी कि इन फ्यूचर हमारे पास क्या चीजें आती हैं। एंड जैसा क्षितिज भैया ने बोला कि अब एक्सपेरिमेंटल पार्ट से ज्यादा हम थ्योरेटिकल पार्ट पे भी काम करेंगे, बिकॉज अब हमें ये पता चल गया कि हमारी थ्योरी गलत नहीं है पूरी तरीके से। तो या, सो दैट इज ऑल। सो आई गेस प्रयोग आपके क्वेश्चन का आंसर आपको मिल गया होगा। एंड या, इन फ्यूचर इसके ऊपर वीडियो आएंगी, एंड इन लाइक कल परसों में ही इस पे वीडियो आएंगे। और मैं इसकी लिंक शेयर कर दूं पेपर की, जो पेपर है, उसके बाद आप लोग जाकर इस पेपर को पढ़ सकते हैं। एंड आई गेस तो अब हमें ये सेशन सम अप करना चाहिए बिकॉज 1 घंटे
हाँ,
हो गए।
because अभी for now we cannot say for sure that there is a new physics. For now it means that we don't have strong evidence for new physics for muon's magnetic moment. तो
नहीं,
अभी
आज
क्योंकि
अगर
हमारे जो
थोड़ा,
theoretic,
या अगर आज ज्यादा कुछ मतलब हमारे पास अनसर्टेनिटी इंक्रीज हो जाती तो हम कह सकते थे, बट अब हम कह भी नहीं सकते इतना ज्यादा श्योर इस चीज को।
all
या
right,
अच्छी तरह कुछ कहते थे।
let's end it and let's dive deeper into the paper ताकि और समझ सके।
Yeah. सो एंड करते हैं सेशन को, तो तब तक के लिए स्टे ट्यून्ड. थैंक यू वेरी मच फॉर ज्वाइनिंग. बाय.
Thanks for the invite, Arjun, and it was a nice session.